So the ultimate strength of a material is the maximum force per unit area the material can withstand before it breaks or fractures. Okay, before the development of the arch, the principal method of spanning a space was the simple post and beam construction, as you can see on the left. A horizontal beam is supported by two posts, required the beams to be closely spaced because of the limited length of available stones and the ultimate tensile strength of a sagging stone beam. So the strength of the material was really based upon the length of the horizontal beam. The semicircular arch, then, developed by the Romans, was a great technological achievement in architectural design because it spread out the force. It allowed a heavy load of wide roof span to be channeled into horizontal and vertical forces on narrow supporting columns. So the stability of this arch depended upon the compression between the wedge-shaped stones. So as it pushed down, the compression of each stone helped lock it in place and reinforce the strength of the arch. The stones are forced to squeeze against each other by uniform loading. The stone surfaces then used in the arches constructed by the Romans were cut to make very tight joints. The resistance to slipping then between the stones was provided by the compression force and the friction between the stone faces. So they acted kind of like a keyway and locked themselves in place. This compression results in horizontal outward forces at the base of the arch where it starts curving away from the vertical. These forces must be balanced by the stone walls on the sides of the arch. So that's why you see in all the old Roman aqueducts and viaducts, what have you, they had this curved support. And they could do that over long distances. The pointed Gothic arch required what's called a flying buttress, and you can see them on the outside here of poor Notre Dame Cathedral. On either side of the arch to prevent spreading then of the arch. The arches can be made very tall then by using this method. So these flying buttresses help shore up the freestanding Gothic arches. If we look at a table here then of the ultimate strength of materials, you can see we have given materials everything from iron to concrete. We're given the tensile strength, which is in newtons per meter squared. Remember, that's force by the area, and the compressive strength, again, by the force by the area. So we've got tensile strength and compressive strength in this table. The density of a substance of uniform composition then is defined as its mass per unit volume. So density, again, we're back to using that little letter rho for density, is mass times volume. So in this density of common substances, we can see that we have for ice, aluminum, copper, lead, uranium, all the way down to the gaseous atoms here, air, oxygen, hydrogen. And so to determine the density, the expected density of any substance, you would refer to a table like this. Of course, it has some caveats associated with it. Notice little a up here, the caveat. All values are at standard atmospheric pressure and temperature, STP, as defined as 0 degrees Celsius or 273 K, and 1 atmosphere, 1.013 times 10 to the 5th Pascal. To convert to grams per cubic centimeters, you multiply times -3. Specific gravity. Specific gravity is a substance is the ratio of its density to the density of water at 4 degrees Celsius, which is 1 times 10 to the 3rd kilograms per meter cubed. So it's a comparison here. So the specific gravity is a comparison to any specific substance or material to that of water at a given temperature. Okay, so it's kind of normalized here, 1 times 10 to the third. By definition, specific gravity is a dimensionless quantity, again, because it's a ratio. When you have units in the denominator and units in the numerator that are the same, they cancel out. If the specific gravity of a substance is 3, then its density, rho, is given by the relationship. 3 times 1 times 10 to the third kilograms meter cubed, which is 3 times 10 to the third kilograms per meter cubed. So that's your density relationship. The force exerted by a fluid on a submerged object at any point is perpendicular to the surface of the object. So you can see by the diagram here, we've got a cube with all these flat surfaces, and you can see that the force being exerted on this cube is normal to the flat side. So top, bottom, side, 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 the other side as well, pushing on it. So it's a volumetric force being exerted on the object. If the object were spherical, you would have an infinite number of forces, all tangent or perpendicular to the surface. The average pressure, P, in the fluid at the level to which the device has been submerged is defined as the ratio of force to area. So we're back to our definition of force per unit area. So newtons per meter squared. The pressure, P, then, at a depth h below the surface of a liquid open to the atmosphere at the top is greater than the atmospheric pressure by an amount of rho gh. So this is our variation of pressure at a depth definition. So we can go back to kind of what we saw when we did our relationships for energy. In this case, we have the pressure, P, times the area minus the mass times the force of gravity minus the pressure initial times the force, the surface area. And we set it equal to 0. So you can see all of these in the free body diagram. We've got the pressure at the open end of the beaker. We've got mg of the mass and the gravity. We've got the pressure per meter square, or pressure times the surface area, pushing up. So everything is trying to keep this in equilibrium. And then we have some height of the object itself. So the mass then is equal to rho times the volume, the density times the volume, which will end up giving us kilograms, equals rho, the area, times the height. The weight, as we've seen before, is mg, then is equal to rho g a h, okay, because we're adding the gravity back into that relationship. So now we have the relationship with pressure, surface area, density, surface area, height, gravity, minus the pressure at the open end of the beaker times the surface area equal to 0. Again, because this thing is floating in equilibrium. The pressure then, if we factor out all of the surface areas, the pressure then minus rho hg, or rho gh, minus the atmospheric pressure, P naught, is equal to 0. So now we can define pressure then at the depth, right here on the bottom, as the atmospheric pressure, P0, plus rho gh, and that value is defined then as 1.03 times 10 to the 5th Pascal. That's atmospheric pressure, okay? So if we had to solve for anything else in this relationship and we had atmospheric pressure, we'd have a starting point. So variation, continuing variation of pressure at a depth. Pascal's principle says a change in pressure applied to an enclosed fluid is transmitted undiminished to every point of the fluid and to the walls of the container. So 1 atmosphere of pressure is defined to be the pressure equivalent to a column of mercury that is exactly 0.76 meters in height at 0 degrees Celsius, with gravity, the force of gravity or the acceleration of gravity, 9.80665 meters per second squared. At this temperature, mercury then has a density of 13.595 times 10 to the third kilograms per meter cubed. So in looking back at our relationship then, the pressure at a depth is equal to the atmospheric pressure plus rho GH, and that value, if we add in then all of the terms that we now know, 13.595, 10 to the third, 9.80665 meters per second squared, and 0.76 meters in height at 0 degrees, we end up with an atmospheric pressure of 1.013 times 10 to the fifth Pascal, or 1 atm, which is our atmospheric pressure. Archimedes' principle states any object completely or partially submerged in a fluid is buoyed up by a force whose magnitude is equal to the weight of the fluid displaced by the object. So if we're looking at some change in the pressure, we let that equal to, in this case, the bulk modulus times divided by the area. Okay, so we have rho of the fluid, GH, times the surface area is equal to rho of the fluid, volume, times gravity. Okay, so we end up then with a term that says rho fluid volume gravity is equal to mass times gravity, which is our weight of the fluid. So we have the weight of the fluid, we have the weight of an object in the fluid equal to mg, which is rho of the object, the volume times the gravity. So these will all be used when we try to calculate through displacement, Archimedes' principle, what the weight of an unknown weight of an object is. Okay, so we have to look at buoyant forces and Archimedes' principle. Case 1, a totally submerged object is usually the first exploration, and then case 2, a floating object like a boat or a plank of wood in a river or in a pond. So when we come back, we will look at defining an ideal fluid.